So I guess my first points, they really continue some of the ideas that Mike mentioned. So if you look at sleep, a lot of it has been driven by technological developments. So if you look on the left-hand side, for example, if you look at the originally commercially available EEG recorder, it used two EEG channels and it wrote EEG on a paper chart. And the paper was provided on a roll, which means it was quite hard to search for events. The second model, seen on the right-hand side, used folded paper, which makes it easier to scan to look for certain periods in time, which lends itself for sleep analysis. But at the same time, this type of analysis introduces a framework, a time framework. So it's discretizing EEG on a time scale. And as we know, those 30-second time frames or pages, they led to the Rechtschaffen and Kale's sleep staging description, and we label 30-second time windows to specific non-REM or REM sleep stages.
Sorry, Dr. Baumert, I'm getting neither your video nor your, let's see. Your video still seems to be off.
It says the host has stopped the video.
Once you, if you don't mind, try sharing again. It shows us that it's off. Okay, here we go. Now we have you. All right, thank you.
And you can hear me, hopefully.
We can hear you and see your slides now.
Okay, excellent. So just to repeat my point, so the way we look at EEG or sleep EEG has been driven quite a bit by technology. On the left-hand side, you see those original paper chart EEG recorders, which use paper rolls, and it's quite hard to locate events. So the second model shown on the right-hand side gives us folded paper, so which creates an imprints a time frame, which led to the Rechtschaffen and Kale's 30-second sleep staging rule. And the cyclic alternating pattern is trying to look more at EEG as a paper roll, if you will. Now, what is the cyclic alternating pattern? So it has been around for almost 40 years. It has been published first in 1985 by Terzano, who's shown in the picture on the right-hand side. And so I've pretty much just copied the description from the abstract. So the idea is that we look at sleep EEG, in particular non-REM sleep EEG, and we ignore sleep stages, non-REM sleep stages. And Terzano found that there are some phases of activity which seem to happen in a periodic fashion. Now, there are some nice illustrations. So this is taken from a review from about 10 years ago. And you see a couple of EEG channels, and you notice there are these bouts of activity as shown here. And Terzano and co, they defined those bouts of activity, A phases, A-like activity, and they are separated by phases of background activity, shown here, also called B phases. And they defined the cyclic alternating pattern as a sequence of A and B phases. So a cap sequence starts with an activation and it ends with before the next activation starts, as shown on the right-hand side. So this is a way to look at EEG dynamically. It's not separated by 30-second scoring windows. Now, when they looked more closely at those A phases, they observed that they are not all quite the same. So if you look at potentially spectral estimation on the left-hand side, you see a potentially spectrogram of an A phase, which has low frequency and high amplitude, versus the right-hand side, where you see an A phase that has high frequency EEG activity, and the amplitude is much smaller. So they divided these activation phases into three types, A1 and A3, and between A1 and A3 is A2, so that's pretty much a mix of high and slow frequency activity. Now, if you want to summarize what those phases could mean, Terzano and co showed that A1 phases, they don't involve much autonomic activation, and it's thought that these A1 phases, they are there to maintain sleep. So they coined this as anti-arousals, whereas A2 and also A3 phases, they are somewhat similar to our AASM arousal scoring. And the idea is, the concept behind those phases is that they are thought to maintain arousability. And like with AASM arousals, those A phases, they are linked to autonomic activation. And it has been shown that those phases, they occur more frequently before sleep switches from non-REM to REM sleep. Now, coming back to the point about technology, scoring cyclic alternating pattern is quite labor intensive. It's not just looking at 30-second windows, but within each 30-second window, you would have to label A phases. So as a consequence, it hasn't been used widely, aside from a few sleep labs, primarily in Italy. Now, a couple of years ago, we tried to develop an automatic A-phase detector or CAP analysis tool, which is based on a deep learning architecture. So it originally used the conventional LSTM architecture. So we look at our single EEG, or we can also use two EEG channels, in particular central EEG leads. And we break it down into windows, we extract features, and then we subject the feature vector to the LSTM architecture, which comprises small memory cells, which are controlled by certain gates. And then we trained our network to create a tool which allows us to detect A phases and perform CAP analysis in an fully automated way. Now we added some additional features. For example, we removed the kinetic field artifact. If you look at the first chart on the top, you see the original EEG, and it looks quite reasonable, but it still contains kinetic field artifact as shown in the lowest panel, which is the difference between the original EEG and the cleaned up EEG, where we used independent component analysis. In our original system, we used a publicly available database that is available on PhysioNet to train the system and to test the performance of our system. So just to give an idea how well the system works, I would like you to look at the LSTM row. So this system was trained on about 100 PSG, so it's quite small for a deep learning system. And the testing data, so the system hadn't seen the testing data, and we can achieve a one score of about close to 90% in the original system. And if you look at the different subtypes of activation phases, A phases, the performance breaks down quite a bit, but it seems to be quite reasonable because the interscore variability among experts is also not fantastic. Since the original description, we have updated our system a little bit, but it's still in the same ballpark in terms of performance. Now, if you're interested in using the system, it's available on GitHub. So the system was programmed by Simon Hartman, who was a PhD student of mine at the time, and it's implemented in MATLAB, runs on MATLAB 2019. There's a runtime version available as well as the original code. So the system or the software has a graphical user interface as shown on the left-hand side on the top, where you can perform batch processing. You just provide the path to all your EDF files, and then we would like to see annotations for conventional sleep staging, which helps us to identify non-REM sleep. So it's not sleep staging is not implemented at the moment. We can perform kinetic field artifact removal if you got an ECG channel as well. It detects A phases, does CAP analysis. It provides an overview plot as shown on the right-hand side, a PDF plot. It provides annotations that you can import into EDF browser, and you can visually look at each of the scored events. It also provides PDF outputs where you can look at every single scored event in a graphical fashion. Now, we use the system to establish some basic properties of CAP because, as I mentioned before, it's been analyzed manually, which means the data usually, or the studies were rather small, so including maybe around 20, 30 people. So we really try to look at CAP in a large population, and we use the Mr. Oz database as well as the studies of fracture database. So both databases comprise older men and women. Mr. Oz is about 2,500, if I recall correctly. SOF around 500 PSG, and we just try to see, okay, what's the relationship between sleep disturbance and the CAP rate, so how much of the non-REM sleep is occupied by CAP. And we looked at the quartiles, CAP rate, and we see that there's a correlation between apnea, hypopnea index, arousal index, and periodic limb movement index, and the CAP rate. So the more of those sleep disturbance you have, the more periodic activation phases you have. And this is shown in both data sets. The effect size is quite small, as you can see by the sperm correlation coefficients. And therefore, in SOF, because the study size is smaller, some of those effects were not statistically significant. Now, if we look at the different activation types, let's say A1, which is meant to preserve sleep, we see inverse correlation following the similar pattern as shown by the sperm correlation coefficients. So the more sleep disturbance you have, the fewer A1 phases occur. If you look at the A2 and A3 subtypes, which are, as I mentioned before, somewhat related to conventional arousals, we find positive correlations, as you would expect, among all three types of sleep disturbance measures, so apneas, hypopneas, arousals, and limb movements. Now we also try to look at the temporal development, so really making use of the fact that we can study dynamics. So we looked at the sleep interval, which is we defined as 90 minutes of consecutive sleep. And we looked at subtype A1, which is shown in yellow, versus subtypes A2 and A3. So we combined both of those. And you can see across time in men as well as in women that the further sleep progresses, the fewer are A1 phases, and you get more A2 and A3 phases, which is what you would expect, because towards the morning hours, people become more arousable. If we compare the distribution of A phases between slow wave sleep and stage 2, we see that in slow wave sleep, we've got much fewer A2 and A3 phases as compared to stage 2, and this is quite similar among women and men. Now, last but not least, the advantage of looking at these activation phases is that we can look at the combination of characteristic across different PSG channels. We can look at heart rate, respiration, and pulse wave, and we derive markers, we derive a time series that gives us some idea about autonomic activation. And we can also perform range causality analysis, which is a way to look at causal relationships between, for example, brain activity and pulse wave amplitude. To conclude, CAP is a marker of sleep instability, and we've developed a tool which performs reasonably well to perform CAP analysis in large data sets. At the same time, the performance still varies, especially if you look at A-phase subtypes. And one reason is that the amount of data used to train systems is quite limited compared to, for example, data sets that are used for sleep staging. Thank you.